Hi, my name is Jack, and today I'll be telling you about a recent paper where we estimated the thermal inertia of soil from how a temperature probe equilibrated with the soil. And as we're getting started, I'd like to thank the Sit-Nasuak Native Corporation, as well as our colleagues who helped in the field, the U.S. Department of Energy, and the NG Arctic project, of which this research is a small part. So let's get started by talking about thermal properties of soil and why we're interested in measuring them. First, there's energy processes in the soil, like the evolution of temperature in soil, how it's affected by sun, and in the cryosphere, how ice forms and freezes. It also gives us some insight into the soil composition, which I'll talk more about later. And if we can measure soil thermal properties, it gives us insight into how soil in general varies over space, which is insightful because in general we can't actually see soil because it's underground. And today I'll be talking about soil thermal inertia, and simply that's the resistance of soil to changing temperature. And actually we have some intuition in that from our daily life. So you're probably familiar with at room temperature, something metal feels colder when you touch it than something that's foam or wood or something. And that's because metal has higher thermal inertia. And the same thing is true in soils, that a wet soil could feel colder than a dry soil, and that's because a wet soil would have more thermal inertia. We can also calculate thermal inertia from the fundamental thermal properties, which are volumetric heat capacity and the thermal conductivity. So we call this a lumped term of soil thermal properties. General problem in subsurface science is that if we want to measure something, we have to dig a hole to get down to that depth. So typically in the field, if we want to measure thermal properties, we have a handheld device like this, and we dig a hole and make a measurement. And our co-author Ian is pretty cheerful about digging holes, but it's a lot of work and it's a major limitation if you're trying to measure at multiple locations and depths. And so the problem that we tried to face is there a way that we can make these measurements of thermal inertia at multiple depths, so image the subsurface without having to dig a pit, which is super laborious. So it sounds like a really challenging task, but we in the end found a way to do it, and I'll describe how we got there. So the first thing we noticed is that we put a thermometer in the ground, and here I've plotted the temperature over time. It starts out warm, like the air temperature on a summer day, and then pretty quickly it equilibrates down and decreases to the temperature of the soil. But it doesn't happen instantly. It takes a few tens of seconds. And what we realize is that the speed that this probe equilibrates tells us about the thermal properties of the soil. So we made a computer model that looks at the rate of equilibration of the probe with the soil, and then calculates the thermal inertia of the soil. And I'll leave the details out here, but if you're interested, you can read more in the paper. So this is great for one location and one thermometer, but what about multiple depths? So we used a special temperature probe that has 15 different thermometers spaced every 5 centimeters along the probe, and we can put this quickly in the ground, and it measures temperature independently at every location, which gives us the equilibration at multiple depths. So for example, here's the temperature curves at every location, and when we scale that data, we see there's a big difference between the different locations, that in some places, this probe is equilibrating quickly, so there's high thermal inertia in the soil. In other places, the probe is equilibrating slowly, so there's lower thermal inertia in the soil. So just like this, we create a profile of the thermal properties in the soil. So we went out in the field and we tested this. We did an experiment where we set up 10 different probes in a circle around one pit where we made ground truth measurements with a handheld device. And you can see that the two types of measurements more or less lie within the range of uncertainty of each other, and in general capture an increasing thermal inertia value as you go down in depth. We also looked at how well this method looks across different locations. So each dot here is a location where we measured with our method and by digging a pit. And we see that our method captures a large part of the variability of thermal inertia in the soil. Another application that we evaluated was using our vertical profile of measurements to capture the structure of the soil. So in this case, you see there's a peat layer overlying some mineral soil, and they have different thermal properties. And so by looking at where thermal properties change, we can guess from our measurements where the peat layer ends and the mineral soil begins. And so when we tried this at different locations, we found that in most cases, this was a pretty accurate prediction of the thickness of the peat layer, which is pretty cool because you don't have to dig a pit to see it. But of course, the method didn't work completely perfectly. There's still a lot of variability that's not captured by this method. And in the paper, we described two main reasons that we think this is happening. First is that the probe heats up from friction when it gets pushed into the ground, and that's not well accounted for by the heat transfer model we made. So this causes a systematic underestimate of thermal inertia by our method. And another unknown in our model is the contact resistance. We don't know how well the probe is in contact with the soil to transfer heat, and so that causes an uncertainty on their estimate. Also in the paper, we talk quite a bit about the connections between thermal inertia and other soil properties, especially between like fundamental properties like thermal conductivity and heat capacity, but also between soil properties like water content and dry bulk density. The details are beyond this video, but if you're interested, please check out the paper. And I wanted to end on one field application we did where we measured at 300 locations, and at each location we have 16 different depth resolved measurements of soil thermal inertia, and it gives a really nice picture of the landscape that would be quite difficult and laborious to make using traditional tools, but we were able to do this in 3 days with a set of these temperature probes. So it really nicely demonstrates the potential value of using a method like this where you don't have to dig a pit. So I'll wrap up with the main points. First, we're able to measure the soil thermal inertia from how a thermometer equilibrates with the soil around it. Second, we identified challenges that are still standing and how future work might address those. And we demonstrate pretty nicely that the method does capture the spatial variability of soil properties and has potential for future work. If you're interested to read more, the paper's out in JGR Biogeosciences. Thank you to the co-authors, and thank you so much for watching.